I was pretty happy with my method here, but then when I looked at the official answers, they do two different methods again. One of which is very quick, but you have to kind of, do a quite a clever little trick. And the other one, again, it used a slightly different approach to me. But I'm going to go through it in my way, and it's going to take long enough, so I'm not going to talk about the other methods, but I do advise you look at them. Now, I personally struggle to sort of visualize what is happening when folding a piece of paper, what the actual shape will look like. So I would strongly advise, like, when you're doing this competition, you are allowed to have blank paper to actually do the fold and see what happens when you unfold it. And what you will get is you'll get your rectangle like so. And when you unfold it, you're going to get a line going like this. And then we can use some of the information to set up the problem. So we know that the shorter side is, well, we're told that the length is 3 times its width. Now, in some of the solutions, they decided to just use 1 and 3, which is absolutely fine. And I should probably use this more in problems because we're just interested in a fraction of the area, it's not going to matter. Um, but I'm just going to stick with how I did it. It's probably going to make the solution a little bit more complicated, but at least I'm kind of showing that why it doesn't matter. All the x's are going to cancel out ultimately. But yeah, if you want to, just go with 1 and 3. I'm going to go with x, and then this whole thing is going to be 3x. So what I then did is I decided to call this P. If I draw a line coming down the middle like this, then for the same reason, this will also be P. And therefore this length here is going to be 3x minus 2p. Okay, these are just some things that we can add onto the diagram. So if you fold the piece of paper back up and kind of, you're going to have to like rotate it slightly, then actually you'll see that we get a pentagon. It might not look exact. Sorry, I'm going to maybe now draw it a little bit bigger, but it's going to look a bit like this. And the first thing to notice, although I've not drawn it to scale, is that this diagonal line is actually this line here on the pentagon. You're going to have to get your piece of paper to see that. And then there's some other things that we can add for dimensions. So first of all, actually, these are both right angles. And I can draw the dotted lines down here. And you can hopefully sort of see that if you turn over your piece of paper. Um, and then if you like unfold it and sort of check, you can actually see that this is P and this is P here. And then the other bit is actually going to be X. This is X up here and this is X here. The 3x minus 2p, if you sort of put it back, yeah, we can't really use that at the moment. But this is quite useful. Um, and actually the dotted line, when we look at the dotted line, we see that dotted line is actually the remaining amount here. Okay, because when you unfold it, they add together. So this bit here is 3x minus p. Okay, and that is essentially our way into this problem to try and work out p in terms of x. So we can use Pythagoras' theorem on this triangle on the right and write down that x squared plus p squared is equal to 3x minus p all squared. Expanding that bracket gives 9x squared minus 6xp plus p squared. Cancel out the p squareds. Rearrange, we're going to get 8x squared equals 6xp. X is clearly not 0, so we can just cancel out an x. I mean, we could factorize it, as a quadratic, but there's no need. We know that x is not 0. And then we get that p is going to be 4 over 3x. Okay, and now we can sort of go back to the problem and replace some of these. There's also one thing I've completely forgotten about. Remember, we're trying to find the area of the pentagon as a fraction of the original area. So the original area is actually 3x squared, the area of the rectangle. So now we're trying to work out the area of the pentagon. That's where I'm headed. Right, so I've got 4 over 3x. Let me replace it elsewhere. So this here is 4 over 3x as well. Okay, and okay, that one's 4 over 3x. Right, here I'm going to get 3x minus 2 times 4 over 3x, so that's 8 over 3x. 3x minus 8 over 3x. That's 9 over 3x minus 8 over 3x. So actually, we found that that is 1/3 x. This length here is 1/3 x. And that is useful because now, remember, I've got a right angled triangle. And let me just draw it out away from the whole shape. I've got x over 3, or 1/3 x. The height of my triangle is x. So I can actually work out this green length. More Pythagoras. X squared plus 1 over 3 x squared. All in brackets. Square rooted. This is where you might say, yeah, just why didn't you just call it 1? This would have made life easier. But I'm going to get x squared plus 1 over 9 x squared. Or, sorry, I'm kind of moving around a little bit, but it's going to be, that's 9 over 9 x squared. So it's going to be 10 over 9 x squared square rooted, which is going to give me root 10 x over 3. Okay, right. I'm now going to draw a dotted line down the middle because I want to work out the area of each of these triangles now. So actually, this triangle is not too bad because it's going to be a half times x times 4 over 3x. And that one's going to be the same. So if I do those together, it's going to be 2 lots of a half times 4 over 3x times x. So these are going to cancel. I'm going to be left with 4 over 3x squared for that shaded purple bit. Right, now I just need to work out the rest of the triangle. I better use a different color. Okay, I haven't used orange yet. Right, I want to work out this orange triangle. Now I have the base actually, because the whole base is what I've just found, this root 10x over 3. Because they're the same, remember, root 10x over 3. So I just need the height. And what I'm going to do is just look at parts of the triangle. Let's just look at the right-hand side. So remember, we had 3x minus p. I haven't done it yet. I haven't put in p is 4 over 3. But I'm actually going to get 5 over 3x because it's going to be 9 over 3x minus 4 over 3x. So 5 over 3x here. And then my base, because I'm just splitting it into 2, is going to be root 10x divided by 3 divided by 2. So root 10x over 6. You might be thinking at this point, why don't let's go read the solutions and see how they did it. But hey, this is a solid method. It's, granted, what I said before about using 1 and 3 would have made life a bit easier, but okay, let's keep going. So the height, I'm now going to need to use Pythagoras' theorem. It's going to be 20, just going to go straight for it and square it. It's going to be 5 over 3x all squared, which is 25 over 9x squared, minus, well, this is not good. It's going to be 10 over 36x squared, square rooted. I'm going to need to put it over a common denominator. So I'm going to get 100x squared minus 10x squared all over 36 square rooted. But this is the height, which is going to be root 90x, because I'm going to get 90x squared. I'm just then separating the third, root 90x over 6. I think I can simplify that. I can bring out a 9, so I'm going to get 3 root 10x over 6, or root 10x over 2. And that's going to be my height. Okay, so finally, if I want to work out the area of the orange triangle, it's going to be a half times the base, which remember was root 10x over 3, multiplied by the height, which is root 10x over 2. That's going to give me 10x squared over 612, or 5x squared over 6. And the total area, therefore, just a little box over here, is going to be that one I had over here, 4 over 3x squared. Plus my 5 over 6x squared. So that becomes 8 over 6. I'm going to get 13 over 6x squared. Right, last step. Remember, the whole area was 3x squared. This area of the pentagon is 13 over 6x squared. So the fraction is 13 over 6x squared over 3x squared. The x squareds cancel. You might say that was unnecessary. And that is going to become 13 over 18, which is D. So I know there's lots of steps, very algebraic. This is a hard question. It's question 23. Just the folding bit is hard enough, and then following through this algebra. So please do look at other solutions to this, not just mine. But it does work. It's a pretty solid method, just applying Pythagoras' theorem, dealing with surds, lots of manipulation. Very easy to make a mistake, of course. But yeah, that's it. Thanks for watching.